Could you hold on a second so Al can get onto the camera?
Good evening, ladies and gentlemen. Welcome to SCI-Arc. Are you ready up there?
You don't have to hold the microphone. You can just talk into it.
Okay. Welcome to the first of two special lectures on designing in space. We're very pleased to have with us tonight Marc Cohen, who's an architect who's been working for NASA for some years. And Marc recently joined the Space Human Factors Office up in NASA Ames Research Center in Moffett Field. It's a fairly newly formed office dedicated to research into some of the crew factors involved in the space program. And Marc's been doing some work on initial investigation of space station configurations. To my knowledge, there are very few architects involved in the space program. I think probably you can count them on the fingers of one hand, is that right? So, just about, he says. Okay. The fact of the matter is that it seems they need our help. The longest space mission the United States has run was the 84-day mission it was the third Skylab mission in 1972, if my memory serves me correct. And it's the one mission that NASA is a little bit sensitive about because the crew actually went on strike about halfway through. That's actually a publicly known fact, but it's one that I suspect they don't like to let out too often. What happened was that the work routine for the third Skylab crew was so heavy that one day they just downed pens and pencils and sat around for 24 hours doing nothing. It turned out apparently that one of the major problems was the actual quality of the working environment. The inside of Skylab had been designed by engineers. The only non-engineer designer involved had been Raymond Loewy, who had basically convinced them to put a window in one end of it, and that was about it. We now faced with a space station program which is going to involve longer and longer missions, and I think one of Marc's group's tasks is to see how it's possible to maximize the quality of the personal environment. I'd also like to take this opportunity to extend our thanks to Marc for his interest and support in getting the Institute for Future Studies here at SCI-Arc its first research grant. Starting next month, we're due to be spending the rest of the year looking at some of the interior design aspects of one of the habitability modules for NASA Ames Center, and looking in particular at the design of the wardroom and the kitchen area. So thank you for that. And I've said enough, so I'll now hand it over to Marc Cohen.
Thank you. Before I start, I'd like to ask if the students who are going to be involved in our project could raise their hands so I can just see where you are. You're all up there? Yeah. All right. Okay. Good enough. Basically, the talk that I'm going to give you is an overview of human factors in space station architecture. And it's sort of in three parts. The first part describes the space station program such as it exists up till now at the beginning of the definition study phase, which really officially got started around April 15th. And we just finished almost a month of continuous meetings in Houston and Huntsville, Alabama to work out what's going on, particularly with our advanced development and research program where we get our funding to do our research that's space station specific. And anyway, the second part of the talk is a description of how we at the Space Human Factors Office define human factors or space human factors, what the components are, what the issues are. The third part will be a description of some of the work that we've done and has been done by at least one other architect working in the space station program. Since David brought it up, I might as well give you the complete who's who of space station architects, not including SCI-Arc yet. But first of all, on Skylab, there were two architects involved. These are people who are degreed, but probably not licensed. Maynard Dalton at Johnson Space Center is an architect who has been probably the premier space station design architect in the United States. He's been involved since before the Skylab program up till now. He's in a very responsible position in Houston, and in fact the reference configuration, which I'll show you at the end of tonight's talk, is essentially his integration design. Then on Skylab there was an architect, Chas Willits, who was actually deputy project manager for crew systems and was responsible for incorporating a lot of the Lowy Snaith recommendations. And to set the record straight, I hate to do this to you, David, there were actually six windows in the Skylab proper plus 5 in the Apollo command module for a grand total of 11 on Skylab. And I'll show a couple of those either tonight or tomorrow night. Then in Boeing has an architect, Brand Griffin, who just moved from Seattle to Huntsville to work on the common module work package for Boeing. And Johnson Space Center has just hired a new young architect, Rod Jones, who's working on general interior architecture, hasn't really gotten very specialized yet. And they have a contract with University of Houston Environmental Design Center, or a grant, who just completed a hatch design study. Langley Research Center has issued a grant to Hampton University in Hampton, Virginia, to do some wide-ranging architectural studies, and they will build some full-scale mock-ups, but I don't really know what the specifics are. And that pretty much scopes out all of the architectural involvement in the space station program in the past and in the present. Chas Willits, I should tell you, is now working at Rockwell, and he's in their space station project office and is involved in their proposals for interior configurations on their work package. So, could we have the first slide, please?
The controls are at your hands.
All right. Okay, I have to apologize. Some of these red slides have faded, surprisingly. I guess this is the microphone, huh? Anyway, basically, the status of the present program is, at least policy-wise, that no design decisions have been made. And that policy is supposed to stay in force through 1986, although we're going to start seeing some requirements being firmed up as soon as probably September or October, which will be pretty strong indicators of some design choices. So right now we're in a period of intensive study, actually which will run through 1986, with a target first launch date of 1991 or 92, ideally on Columbus's, the 500th anniversary of Columbus's birthday or his landing in America, if you like that type of game. And basically, Johnson Space Center has a majority of responsibilities located there, with support at Marshall Space Flight Center, Goddard Space Flight Center in Greenbelt, Maryland, and Lewis Research Center in Cleveland as the primary work package contracting centers, and support from the research centers, NASA Ames Research Center in the San Francisco Bay Area, Langley Research Center in Hampton, Virginia, and Jet Propulsion Laboratory here in Los Angeles. But I will be talking essentially about the work we're doing at Ames in space human factors. Now, the composition of the space station program you see described there on the other slide, the blue slide. There's a manned core of the station, and there are other components. There are unmanned co-orbiting platforms and a lot of peripheral elements, and also future growth. And these are particularly significant from the operational point of view. And tomorrow night I will be talking extensively about proximity operations requirements for windows and workstations, which we are doing some research in. Now, Skylab was the United States' first space station, It had 3 crews, the longest mission of which, as David said, was 84 days. Each crew had 3 crew members, and they were all male and all pretty much came out of the traditional test pilot sort of school, although I think we had one MD fly on it, Joe Kerwin. Anyway, the basic characteristics of Skylab, which are important to understand. Do you have a pointer or anything like that? Should have thought of this before. Well, anyway, I'm in danger of walking off the stage here. I wonder, is this building like an exhibit of code violations? Anyway. Anyhow, the major components of Skylab were the Saturn workshop, which was a Saturn V upper stage booster. I think you need some new batteries. I have some in my briefcase, actually, if they're pen-like batteries. But anyway, this was the Saturn workshop. It comprised the, can we focus this a little? The crew quarters area here and the dome area, which was a large line. The diameter of this was about 22 feet exterior and about 21 feet clear interior. There was an airlock section for going out EVA, which used a surplus Gemini hatch. There was a multiple docking adapter section and the Apollo module, command module and service module. This section here was the Apollo telescope mount. It was a solar telescope. It had its own solar arrays, and these were the intended arrays for Skylab. Now, if you don't know the history of Skylab, I'll refresh your memory for you, which was that on launch they had an accident, which was that the casing fell off. They lost one of the solar arrays, and the solar thermal protection screen was torn off. And what you see deployed there on the surface is a canopy that was deployed by the first crew to go up. It was the first emergency EVA ever performed. The station was launched unmanned. The first crew came up in an Apollo command module dock. The internal temperatures were close to 100 degrees because they weren't getting the cooling and they were getting a tremendous amount of direct radiation. And they rigged this parasol over that to reduce the heat load. And after that, the ambient temperature inside was reduced to about 82 degrees. Now, here you see an astronaut out EVA doing work on Skylab. And of course, we also had a lot of EVA experience on the moon. And tomorrow night, I'll be describing some of the Ames activities in EVA, extravehicular activity. We have the lead development for suits in NASA, in-house development. And we also have an airlock study that I'm completing. All right, there are certain assumptions in this program that are important to understand. The first is that all parts of the station will be launched in the shuttle payload bay. And this bay has some very critical dimensions. 14 foot, 0 inches maximum outside diameter for the module or payload. And there's roughly a 45-foot maximum practical length to a module. The bay itself is 60 feet long, but in terms of getting things in and out, you need a shorter module. The station itself will fly in low Earth orbit at about 200 to 300 nautical miles at a low inclination, about 28.5 degrees. The power will be solar photovoltaics of some kind. There will be a zero gravity station. This is a question I always get. Why aren't you going to have artificial gravity? And the answer to that question is because nobody wants it. There is not a single scientific payload that's going up there for general use of the station that wants artificial gravity. What virtually all the researchers who are concerned with gravity want is the best isolation from vibration and gravity they can get. The only exception of this is that some of the life sciences researchers want a small centrifuge on board so they can maintain some of their animals at a controlled gravity of 1g or partial of some fragment or fraction of 1g. And we have a budget which is right now being hotly contested. We have a schedule, and I'll just show you where we are. We're right here at the beginning of the definition study phase, known as Phase B. We're right here between the beginning and the first major milestone, the intermediate requirements review, and the grant that we're giving SCI-Arc. We hope to have at least a final draft in time for that milestone. So that's actually a pretty short fuse, you'll notice, relative to what's going on. But you can see that the conceptual development phase, or Phase A, and definition study are both relatively short compared to the design build phase and the operating phase, which will also include additional growth points. And this one is a diagram of the cluster concept with the manned base and the co-orbiting platforms and polar base and so on. Now, I will start to give you a little taste of Ames's involvement, my involvement. I first started in space station architecture about 2.5 years ago when I was in the engineering division. I started out as a legitimate architect at NASA doing facilities work, principally wind tunnels and life science laboratories. And when the space station program began to percolate, I managed to freelance some work and write a paper on geometry for space station, developed this triangular tetrahedral concept. And eventually, when we did form the Space Human Factors Office about 9 months later, became a charter member of it. Anyway, the characteristics of this concept were that it was the simplest platonic solid. With just one triangle, you achieve a racetrack, which means a complete loop for circulation. It has 4 hubs and six modules potentially docked. This is a berthing beam here, and designated crew quarters modules and lab modules and a workshop module. And I'll show you more of this later on. This is just to let you know how I got into it. And after doing that work, the Phase A Concept Development Group was established at NASA headquarters in Washington, and almost by accident I became a commuting member of that. And we had meetings like every 3 weeks in Washington, and there were 3 people from Ames going, and they needed someone to fill in, so I went once, and then I wasn't kicked out, so I ended up going again and again through Phase A. So the Concept Development Group developed a thing called an initial operating capability model, and this is important to understand as sort of the operational or performance boundaries of the station in the broadest sense. First of all, autonomy. The basic autonomy baseline is 90 days on orbit without a shuttle revisit. That's 90 days of being self-sustaining, essentially. 5 days without routine ground support. That means without needing to get any routine instructions from the ground on what to do. And 24 hours without any communication at all. That pertains principally to downlinking scientific data. And there's another timeline which was originally 21 days. I've just heard it stretched to 28, which is in the event of some type of catastrophe or accident, a capability for a safe haven mode of survival, which is basically camping out under austere conditions, assuming major failure of a life support system or something like that. And this is based on how long it would take to turn a space shuttle around to get back to the station to effect a rescue. The crew for the IOC is 6 to 8 people on 90-day tours, and the crews will be quite heterogeneous with a mixture of pilot, mission, and payload types. One of the greatest departures from popular image of spacecraft is that there will be no bridge. Command and control will be completely distributed throughout the station. There will not be a bridge like in Star Trek where Captain Kirk sits on the bridge of the Enterprise 8 hours a day in a chair and gives orders to people. We don't have the personnel to do that. We don't have the resources to do that. What we will do is have a command and control console located in each major module, and the mission commander or the station commander will be able to respond wherever he is to the system if an alert is enunciated or if there's a need for his attention. And hopefully the station will fly itself, will be autonomous enough that the pilot or the commander will will not need to devote much of its time to flying the station. It will essentially fly itself. There you see another sketch of the space station cluster concept. Now, one of the most critical limitations as far as an architecture is concerned in terms of the habitable volume is this space shuttle cargo bay dynamic envelope. And basically, what you see here on the left is the minimal common module that was defined by the concept development group, which was then described in detail in the reference configuration description, which became the basis of the request for proposals. It ended up being stretched to a 35-foot minimum, but this is really the smallest we ever considered going. And there you see the 14-foot diameter, 4 feet clear. In this case, 18 feet long. We used a nominal planning segment of 9 feet. And here you see the conical end caps, safe haven pack. There's the distributed command and control console. And life support in each module, ideally. Now, this module has to fit into the cargo bay. It's supported on trunnion pin fittings along these rails. This is a computer graphics sketch of that 2-segment module plus a portion of a solar array packed into the cargo bay. This is a transverse section of it with some type of propellants attached. I guess you see them right over there, attached to the common module. These are cryogenic and propellant storage tanks. Now, during the concept development group, we did a lot of quick sketch studies of how we would work with this minimal module, how we could put them together into configurations. This particular one is a docking adapter module we call the multiple berthing adapter. It had a small airlock for going out EVA. We called it, it's a crew lock, which is a concept originally developed by Bill Haynes of the Aerospace Corporation. You'll see more about that tomorrow. I bastardized it here to a great extent. He almost never forgave me for that. You'll find out why tomorrow. And you see a suit servicing support facility there. On the other side, you see a sort of a bundle configuration that we proposed at one point. And actually, I found myself falling back on the triangular tetrahedral configuration as I went through this process, proposing this as a minimal IOC with 3 modules and 3 berthing hubs, and the potential to build out indefinitely from that structural core. Here you see the basic module idea where I'm using a hemispherical end cap at 12-foot diameter, conical adapter ring, and cylindrical module segments, and got a lot of mileage out of this type of shell geometry. Here you see an early attempt at a window workstation, which is a bubble dome attached to a berthing port. In this case, the port's at 60 degrees, and where you see the ports over here, you see that bubble over here in plan, supporting a remote manipulator arm. By the way, if you have any questions, please don't hesitate to ask. I'd rather you ask them as we went along. Just shout them out rather than dozing off and forgetting them until the end, you know. Anyway, as we went through this process and we looked at what we were dealing with, and we found that the 2-segment modules were not really big enough, we said, well, what if we fly them up and join them together as if they were one long module? So as we went through the process, the whole thing got more and more Baroque, as you can see. And you know, I kind of revisited the demise of the Renaissance, you know, in terms of the decay from high Renaissance to Baroque to Rococo, you know. Anyway, you can talk to architects about this sort of stuff, but you can't talk to engineers this way. And in fact, I actually learned a remarkable lesson when I was working in the engineering division, which I did for about 3.5 years on ground-based facilities, which is that aesthetically, you can do almost anything you want so long as you don't say anything about it. So long as you don't say anything that forces it into their consciousness, because they don't like to be conscious of things, you know. And But I got away with some great things. I put a Palladian archway in our travel office, and no one ever said a thing about it because I just did it, you know. Just never asked anybody. So that's what you basically have to do in this situation is you have the idea and you present it and do it and argue for it in functionalist terms and in logistical terms and whatever else is within the language of the engineering culture. And so far I've been getting away with it. And anyway, we also went through a lot of exercises to look at the launch build-up configuration. So here you see the first launch and the second launch and the third launch and, I don't know, the fifth launch. And then finally 7 and 8 launches to get the full configuration there. Obviously this gets too complex and it's better to have a single larger module on each of the sides of the triangle. So this evolved. I looked at a variety of other configurations based on the triangle. Did a number of detail studies such as this hatch diameter analysis, asking questions like if you have a rack you need to bring through that has a certain maximum dimension, how big an opening do you need and what's a tolerable amount of clearance around that, and so on. And built a lot of quick models. We had a phenomenally large budget at the time, but this is a high-class model. These are Fabergé hair curlers. And anyway, here you see a variation on the triangular space station berthed to the space shuttle, flying in gravity gradient mode with solar array and so on. Now, that basically concludes the section describing really how we got to phase B in the space station program, at least at Ames. And we formed the Space Human Factors Office really almost a year and a half ago. It seems like it was yesterday. I mean, it's really, things have moved so quickly. But we've been developing our definition of human factors. So the first and most important thing is that we're talking about working and living in space. This is an environment different from the shuttle, which is just a, you know, which is a vehicle. You know, it goes up, it goes down, it moves around. The station is going to be essentially stationary in an orbit in the sense that it has a fixed relationship to the Earth over a long period of time relative to the shuttle. With a major goal is to maximize human productivity. That's become the buzzword of the year. But what that involves is crew performance, maximizing the internal vehicular activity time, crew time available for payloads. We want them to have hopefully 80% of their working time available for payloads, which compares to Skylab, which is where they only had about 50% of their time available. That may not seem like such a big leap, but if you look at the opposite of that, we're talking about reducing maintenance time. It's just time spent on maintaining the station, reducing that from 50% to 20%. And we're looking at making EVA routine, and really the mission requirements are looking like about 1,500 hours a year. Now this compares to a total EVA experience of about 350 hours over the past 20-some years that we've been doing EVAs. So we're going to have like 5 times as much EVA in the first year of operation as we have had to date. This is several orders of magnitude improvement in capability that we need. And we're taking that seriously in our AX-5 suit development program at Ames. We have new space mission characteristics, the long duration, repeated tours of duty, permanent habitation with high levels of automation and machines and robotics. That adds up to autonomy. Now, you'll notice I'm going to use some slides from Colonial Williamsburg, and the reason I do this is to demystify the idea that space, we're living and working in space, is hard to comprehend. It's only the realm of high technology. Basically, the way we see it is that we're at a stage in the commercial and industrial use of space that's quite analogous to the beginning of the Industrial Revolution, say the 18th century, where the dominant mode of production was cottage industry, where you had people working in a small shop close to their home or right within their home, working 1, 2, 3 people at a time, doing things individually, running experiments, doing materials processing, really on an individual piecework sort of basis. And that's what you see here. So I think we have precedents in our experience on Earth for what we're about to go through. And we have a lot of other issues that bear relevance to this analogy. We have a lot of concern for safety. In the concept development group, we devoted a tremendous amount of time to the safety issues. I won't overload you with those tonight, but we're going to have, in materials processing, we're going to have forges that are or ovens that are going to involve using a tremendous amount of heat that we have to use and dissipate. We will have potential for contamination. We'll have products of combustion that we have to handle. Very similar to certain industrial types of facilities on Earth. And the contamination problem and heat problems in particular are quite difficult problems. We have a crew safety human factors model that we developed, and I won't go into this in any great deal of detail except to say that basically we see habitability is critical for productivity and safety, and that basically deficiencies in the environment or stresses in the environment can lead to degraded performance, which can ultimately lead to a safety hazard. I think I'm going to need a glass of water at some point here. I'm sorry, I did a long pitch at Rockwell this morning, and combined with the beautiful air you have here, it's really getting to me. Anyway, so we're looking at countermeasures against stress, and in architecture we're talking about design measures, privacy, windows, and then in various other areas we have countermeasures as well. There you see Pete Conrad on, I think, the second Skylab crew using the shower. So hygiene is, for example, a major sort of countermeasure against stress, and so on. Some of the major stressors are confinement, isolation, and separation from the ground, and we see social countermeasures to that as well as architectural countermeasures. One of the interesting things we learned in this study was that sometimes the countermeasure to one sort of social thing can be found in an area outside of sort of the immediate purview of the social field. And that is Tektite, which some of you may have seen in San Francisco when it was sitting at Fort Mason for a couple of years. It's just about the size of a two-segment common module in each of those cans. It was an undersea environment that I believe is now being put back into use. Another major factor we deal with is zero gravity, or really microgravity, where the crew experiences the sensation of weightlessness and really changes a whole lot of the common assumptions we have about posture and position, and your actual physiology changes too in interesting and unusual ways. Now, architecture. When we talk about space station architecture, we take a definition that fits within the human factors discipline. Thank you. Back up. Great systemic redundancy, that's what we're always after. Anyway, the definition that we've adopted as a working definition is Richard Neutra's definition of architecture as a social art. It becomes an instrument of fate because it not only caters to requirement but also shapes and conditions our responses. It can be called reflective because it mirrors a program of conduct and living. At the same time, this art of a planned environment does more. It also programs our daily conduct and our entire civilized life. It modifies and often breaks earlier established habit. Well, this is remarkably relevant to what we're hoping to do with the space station. We're breaking earlier established habit, particularly in the shuttle, which are basically short flights where the crew camps out under very austere conditions, and we're looking at an environment that will program conduct and living. On the right you see a lighthouse at the north end of Campobello Island off the coast of Maine, actually between Maine and New Brunswick. And this is an interesting analog to a space station. Nobody's really looked at lighthouses, but it has certain interesting characteristics aside from the very striking form. I think this is east or west Quaddy Light, I forget which. But anyway, it has very remote, difficult access. It has observation functions. It has a sort of an orbital transfer vehicle hangar for transportation or escape, rescue, and it has permanent habitation in this remote environment. So there are a lot of analogs that we do study, principally oil platforms and submarines and ocean racing yachts and other previous space stations or spacecraft. Now, when we talk about architecture, we're also talking about physical form, of course. This is often called configuration, and I will describe some of the thinking that went on about configuration in the concept development group. What you see on the right are what they call basic space station geometries in this chart, but what they really are solar array support structures. In each of these cases, we have a different way of supporting a solar array, and they don't have a whole lot to do with what the how the modules are connected together. And one thing you'll notice from these things is that the solar arrays are really quite large relative to the surface area, at least, of the modules. And structurally, what we're really dealing with in terms of dynamics is hanging a small, heavy weight off of a very large solar array. The solar array will have enormous moments and torques on it, but it's a very light structure, and we're hanging this small, dense weight of the cans, of the habitable modules from it. And there are a variety of situations here. This one really is, what it is it's a gravity gradient mast-supported structure. This is a rotating, very large wheel with solar arrays mounted on the outside, and the module's almost invisible. They're so small in the middle with external tanks of the shuttle that use this intermediate structure. This is a Grumman and Boeing concept. This is a Hughes concept. This is the power tower concept, where we have a large tower supporting the solar arrays flying in gravity gradient mode, Earth inertial gravity gradient. And this is actually a Langley Research Center concept. This is the McDonnell Douglas / concept CDG-1 concept. It was adopted as a baseline for the concept development group. This is a streamline, so-called streamliner Big T from Johnson Space Center, and this is the Delta configuration from the Johnson Space Center Structures Division. And they all have interesting characteristics, but as far as what their advantages and disadvantages are, but what I would point out is that's just one aspect, the solar array support approach. We also have to deal with the module connection pattern, which is also an area that's been worked out in a lot of detail. The module interface strategy is the attempt to connect all this together, and you'll see how that worked out in the reference configuration to the extent that it has worked out at all. But the interesting thing that came out of this study was that the differences between the configurations are most clearly understood in terms of the connection and assembly requirements and hardware. And I'll talk more about that later. Here you see the module connection pattern study that was done by the that particular study group at the CDG. I think they chose 10 configurations or connection patterns for final evaluation there. I was flattered that they chose 2 of mine out of the 10. And while I don't really claim to understand the choices they made in these grades, I'm going to have to move over to see this. Basically, what they did here, you'll notice that these kind of rectangulated ones without a racetrack, with just cantilever modules, got the highest letter grades. However, in the sort of the true-false section of this, they completely fell to score. On the other hand, those modules which do meet the true-false requirements better get much lower letter grades. And so we're dealing with this type of complexity and contradiction here. Not necessarily in the sense that Robert Venturi meant it, but just in terms of function. You know, we don't have to look at facades, you know, hokey facades to find complexity and contradiction. Just because something has functional pretensions or functional requirements doesn't mean that you have problems with your complexity and what its logic is. Now, this on the left is a matrix that attempts to work out the module interface strategy, comparing the solar array support and module connection pattern. And at the CDG, this was the closest anyone got to anything meaningful, and it really doesn't tell us very much. So this is a problem that we're still struggling with to a very great extent. And we still have a long way to go with it. Okay, now volume is something that we have identified as the most critical single human factors and single architectural design issue. It's severely constrained by the external limits of the station module. It affects the entire habitability situation. And there have been a lot of studies of volumetrics and habitability. The first one to do this was a guy named Celentano about 22 years ago, worked for North American Aviation at the time. And he proposed an idea that you have a graph of cubic feet against mission duration, and the idea that there's a minimum tolerance level and a performance, an optimal or acceptable performance level. And you can plot out various precedents along this graph, and hopefully we're going to be up somewhere above or on this performance curve. And that's Rockwell only because North American Aviation was taken over by Rockwell, and it's their idea. The efforts to reduce cost we were constantly fighting efforts to reduce cost by minimizing volume. We believe this presents a false economy that creates a lot more problems than it solves. The effects of inadequate volume are forcing miniaturization of many items, precluding a lot of off-the-shelf hardware, impeding or preventing on-orbit maintenance, and really making everything much more difficult. Now, spatial orientation is an interesting problem. At the time that I prepared this portion of it, I hadn't completed or even started a lot of the research that I'll be showing you tomorrow night, but this will give you an overview of kind of a geometric breakdown of some of the issues. We found that it's possible to establish a reference orientation with 1, 2, 3, or 4 point sorts of geometries. Now on the right here you see a slide from Skylab where somebody's getting a dental examination, and you have to ask the question, who is right side up and who is upside down? Well, as fate would have it, the dentist there has his elbow on the wardroom table, so nominally speaking, he's right side up and the other guy's upside down. But this is really a very difficult issue, and we're just beginning to get a handle on it. We hope we'll have some good answers by the time we need them for the major milestones. But anyway, we found precedents for all those spatial orientation cues. But let me just show you this chart quickly. This shows 4 different ways of breaking out an identical configuration of shell structures or habitable volumes. In this one here was the first, was actually proposed in 1979 as the initial Space Operations Center concept, where up is straight up. Here's the same configuration with up the short axis, equally consistent and logical. Here we have all floors coplanar, and up being straight out of the screen towards the audience. And in this case, up is away from the center, and turns out that all of these have been proposed in various ways. All of them have advantages and disadvantages. Now, in Skylab, there were 2 major sections. There was the Saturn workshop with the crew quarters module, crew quarters section here, which had a clear up-down local reference, and there was the multiple docking adapter section, in which there was no clear reference, and this was called the 0G section of the station. The equipment was basically packed almost at random against the sides. Skylab was a very fast crash project, used an incredible amount of Apollo and Gemini surplus hardware and other goodies like that. And when they furnished this multiple docking adapter, they just tacked the stuff to the walls, and very little thought was given. But the effect of this was that many of the crew members found it reported disorientation and confusion when they entered or left this module as to which way was up, or to find controls or boxes, or at this Apollo telescope mount console. And so that was a serious issue. Whoops, let me go back here. All right, so going back to the idea of defining the geometry by 1 point or 2 points, We have a precedent from the Soviets, which is that their EVA training protocol is that up is always away from the station, down is towards the station, and then they use a polar coordinate system for location. In both Spacelab and Skylab, in the Saturn workshop, we had an up-down two-point reference system. In the RAFT proposal, which we've had from both Grumman and Boeing, we have up-down, but you also have the possibility of defining fore and aft within the RAFT, where modules are joined together side to side. And in the Delta configuration that I showed you earlier, in this case, it's shown with the modules at the outer edges of the triangular prism. There's actually two consistent ways, minimally, of defining up in a consistent way. It gets more complex. Obviously, we need a way of evaluating and selecting choices in this area, and we're researching that. Circulation is another major issue, and in studying circulation, we found it remarkably similar to the issues you find in building code requirements for fire egress. And we've identified properties of access, multiple access, egress, and dual remote egress as being perfectly transferable to the space station environment. Now, in Skylab, we saw some interesting characteristics of circulation, which I think are described on the next slide. We also looked at biological analogies for circulation. Let me go forward over there and there. Okay, on Skylab, the key circulation characteristics were that obviously circulation connected each section of the station to the adjacent ones. However, the through circulation, the through penetration, created a serious traffic flow problem. Even though there were only 3 people on here, the fact that somebody might be working doing sensitive observations at the Apollo telescope mount workstation, if somebody came through from the command module or carrying a piece of equipment and bumped into them, that was very disruptive. Even if a crew member was carrying nothing and just bounced through or translated through, as they say, it was considered disruptive. So that's serious consideration for sensitive workstations. Finally, the airlock was situated here in the middle, and when an astronaut threw out EVA and that airlock was depressurized to vacuum, it effectively cut the spacecraft in 2 separate pieces, and if a crew member were here and there were some emergency, that crew member would have been trapped with no way of escaping to the command module. We should have learned from this for the space shuttle, but for some reason that I still don't understand fully, we ended up with a space shuttle that replicates this mistake, where when the space lab is in the cargo bay, you have to pass through the airlock to get to the space lab. So if you do an EVA, you have to evacuate the space lab of people, or the people could be cut off from transit into the forward crew quarters. Now, privacy is a very important issue here. B.J. Bluth calls it essential for staying sane in space. And in looking at privacy, we have a lot of research going on. I personally have tended to shy away from the sort of the sociological and psychological measures of it, simply because I think that privacy is more than what the environmental psychologists call personal space, although certainly there's value in that type of research when you're dealing with groups. I have found Vitruvius's definition that privacy is defined by invitation, who can invite somebody into their space, as really the critical issue. And it's not just people, it's being able to control the admission of light, noise, information, and fumes, anything like that, are all key components of privacy. There's also an aspect of community control that bears on privacy, which is very well described by Christopher Alexander and Chermayeff in their book Community and Privacy, where they look at entry lock. I've translated this into an analogy, into the space station analogy, but direct access to the exterior, buffer between private domains, a lock to overall separating the private crew quarters from the from group activity areas, similarly for the common areas, and external separations and clearances. I think all of these are fairly relevant issues that we still need to deal with. That other slide, by the way, showed, whoops, wrong way. Showed, I think that's Pete Conrad again, in his sleep quarter on board Skylab. These were quite small. They were about 3 feet by 3 feet, and they were really little more than sleeping bunks. There wasn't enough space in there for any sort of private desk or even much personal article storage. But Skylab was so small, there was really no storage problem. Let's see, where are we? Okay, more of the CDG period sketches. Here you see that minimal common module with 4 crew quarters and sleeping restraints. These are about 5 feet by 4.5 feet. And very interestingly, this figure of about 22 and a half square feet, we did a literature search for prisons. What's considered to try to find out what is considered the threshold for cruel and unusual punishment. And it turns out that the maximum we can hope to achieve here is defined by the Supreme Courts of several states as constituting cruel and unusual punishment in a prison in terms of square foot per person. Obviously, we have very different organizations or institutions. However, you ultimately, in some sense, have the physical constraint, the physical volumetric baseline that you have to be aware of in terms of the messages you get from the environment over the long term. And then you also see a wardroom galley there. And one of the things SCI-Arc will be looking at, principally what SCI-Arc will be looking at in their grant, is the social architectural aspects of the group gathering places, the wardroom galley, an exercise area, and other activity spaces within what we call the group activities module. And here we have it. We're basically looking at the galley, the dining area, recreation, entertainment, and group work areas of some kind. Some of the group workstations will not be explicitly part of the habitability module, and we'll have to get some determination of what activities might be particularly excluded from social living areas or private living areas. And we also have questions of what sort of small group activity area do we need. One of the key issues that we need to deal with is what is the relationship of the galley to the dining area? Do you have the galley right there with the dirty dishes or whatever piling up? And there are a lot of social issues. Who does the cooking? Is it cooking rotated? Do you have one person who does all the cooking or all the cleaning up? We don't really have any answers to that right now. One thing we do feel very strongly about is that it's very important for the crew to share as many meals together as possible, or at least one meal a day. The Skylab astronauts reported that was the high point of their day, the one meal when all 3 of them got together, and we think it's very important for maintaining team cohesion. And another issue we have is how much amenity can we provide, how much do we need, from one extreme of austerity to the other of opulence. Obviously, we would fall somewhere in between, but we're always afraid we're going to fall at this end or further. Visual systems. Visual systems is kind of a catch-all for anything that has to do with seeing and its character and its effects on the environment and on the spacecraft. We deal with windows for work, rendezvous and docking, celestial or anti-Earth observation, and Earth observation. And tomorrow, a major part of the discussion will deal with windows for proximity operations. Windows for entertainment. On Skylab, the most popular pastime was watching the Earth through the 18-inch wardroom window at the mid-deck in the crew quarters. And similarly on most other spacecraft, and the Soviet Salyut stations, they've reported that as well. We've got to deal with window location, type and size, closed-circuit TV and video, and we have another problem, which is radiation admission, and also meteoroids and contamination. This is a view through shuttle windows of various approaches to the different space station configurations, and This just demonstrates the importance of view angles. These two represent the same space station configuration from different views. And obviously, the view that you use the view angle can be very significant. Windows have other characteristics in terms of observation and admitting light, looking out and what visual energy light energy passes in. And one of the things you'll notice is that in terms of plants, we're quite serious about eventually growing food on orbit and making use of direct solar radiation or piped solar radiation to do this. We have to deal with lighting too. And we have an awful lot of precedents you can see everywhere. I mean, not precedents, but cases all wherever you go of really lousy lighting design. You don't have to look very far to find it. But this is not a technology issue, really. I mean, except unless you're talking about balancing full spectrum and ultraviolet, which is really a very subtle thing. This is a Louis Tiffany interior recreated or assembled in the Chicago Museum of Art and Industry. It's, turn of the century technology, but it's a wonderful environment. It's totally interior. There's no outside light. But he does wonderfully well with this. There's no reason we can't take advantage of these design skills. Exterior illumination is another major issue that we don't know to what extent we'll be able to deal with it at this time. We have the issue of sunlight flash over the horizon every time the orbiter goes around the Earth right now, or the station. Once every 90 minutes you get a tremendous flash of sunlight. And in fact, we had one thing that I actually haven't ever been able to substantiate. I should try a little more, which is that when the astronauts were doing the Solar Max repair, this is pure hearsay, they had something like 22 screws they had to remove, and they lost 2 of them when they were putting them back. And the rumor is that they lost them during the sunlight flash, during a sunlight flash over the horizon. So anyway, that's something to think about. It might not be, some super redundant screws the next time. Also, external illumination against the night sky. Vibroacoustics is a very key problem. The center with principal responsibility for researching that is Langley, but you've got to understand the situation, which is that in space there is no outside atmosphere to absorb sound. For example, the sound and the energy of the sound of my speaking to you, most of it is actually passing out through the walls and windows of this building and being absorbed by the atmosphere. On a space station, there is no atmosphere to do that, and what will happen is the sound energy will bounce around inside the station and reverberate until it's all converted ultimately to heat. And therefore, on the shuttle in particular, we have a serious noise problem. At one point, the Columbia, the first orbiter launched, had flight deck noise at about 85 decibels, principally from the lack of good isolation vibration in the fans, the ventilation fans for the avionics. That's now down to 70-something decibels, but it's still pretty loud on all the shuttles. We had the opposite experience on Skylab, which was that it was so large that it was very quiet, and this created a problem for the crews to sleep. The original plan was that the crews would work in shifts. One guy would be up all the time, one would be relaxing, one would be sleeping. It turned out that just the noise of a crew member moving around the Skylab, and particularly of flushing the toilet, was so loud that it made sleep impossible. And so consequently, the crews all went on to a single shift. There are a lot of countermeasures that are being applied to this, and I think we should be able to lick most of the vibroacoustics problems. But one of the things that we can't use is a sort of absorbent materials that are commonly used on Earth in acoustical ceilings and carpets, because of the fact that we're always worried about off-gassing, flammability, and particulate contamination. Structures and structural shells. I'm going to principally talk about structure here in the context of the module pressure vessel, which really has a significant influence on the habitability of the module is the issue of whether the wall is smooth or ribbed and how you attach things to that wall. It's a very strong preference for having a smooth wall with minimal attachment points to that wall as a way of minimizing accumulation of dust and contamination, and also not having permanent attachments to the exterior walls at any place so that we can inspect the wall from the inside for damage or stress or fatigue. And so I looked extensively at the end cap geometry to support the berthing ports and mechanisms and other windows and other things. Looked at the methods of fabrication and reviewed the forms, and I'll be talking about end caps in a great deal more detail next, well, tomorrow night. So there you see the shuttle on its launching pad. And let me explain how I got into the whole end cap issue, which is that we at Ames have the life sciences payload preparation group that just flew the rats and monkeys, and I guess we just had rats and monkeys. Somehow the frogs' eggs got bumped, or at least we didn't hear about them on this last space flight. And I will not take any questions about the ventilation system problems. Actually, it wasn't really a problem after a few days. But basically, what happens is when they load the animals into this, they allowed the animals 24 hours before the flight, and they go through this boom bridge into the mid-deck hatch and into the mid-deck area of the orbiter. So what they have to do is then go, this is the orbiter cargo bay shown vertically, go into the airlock through 2 right-angle turns, down the tunnel, down 1 bosun's chair, a right-angle turn, down a 2nd bosun's chair, and then the animal in its cage is inserted into the Spacelab rack. That's very time-consuming. It's probably traumatic for the animals, and it's a real pain in the ass all around. So some of the people in our groups asked me, isn't there some better way we could do this? And the idea I had was very simply to install a hemispherical end dome with a hatch at some angle, here 60 degrees, and simply enter it directly and just use 1 bosun's chair, not have to go through the mid-deck. There's a couple problems with this. One is that the cost estimate for making this modification is $100 million. The reason for that is that within the cost estimating system that's used for preliminary design in the space station program at that time anyway, and it hasn't changed very much, is the smallest unit of measure we use is $100 million. During the concept development group, we had this $8 billion budget, and it was run by Luther Powell of Marshall Space Flight Center, and his charge to the group was to not look at anything that had a cost differential of less than 100 million. So in the folklore, we have a new unit of currency, which is 1 Luther, $100 million. And eventually, our arguments degenerated into sign language at certain points where you'd point to something and you'd hold up 1 finger, and Luther would shake his head, no, hold up 4 fingers, and meaning he thought it would cost 400 million, and you say, no, it'll cost 100 or 200 million or less, whatever. But that's one of the things, it makes it hard to think about going back into conventional practice. I don't know if I could ever handle anything that was less than about $5 million a square foot. Anyway, the reason for these costs is that obviously the machining and fabrication is expensive, but what's really expensive is all of the certifications, the reliability, quality assurance, maintainability, testing, and systems integration. In any piece of hardware, over 50% of the budget, well over 50% of the budget goes into those certification processes. And that doesn't matter whether, that we're talking about something, a detachable, separate piece of hardware, whether it's a tunnel or the whole module, you get this enormous tax. So the first station module I applied this to was the logistics module, where you see this hatch at on the side of the orbiter in the cargo, on the side of the module in the cargo bay. And this is really one of the poorest attempts. It has these gas bottles around the middle, That's not really a very good arrangement. Requires too many different types of shapes. But this is the way I got into working with the endomes. And here you see a development of the multiple docking adapter type of module into a combination of a docking hub and a sort of a workshop module with a suit servicing and support facility and an airlock, in this case, at the end of the module, and a remote manipulator workstation. And there you see it in plan and so on. On the right, you see three variations on airlock using this geometry. Here it's a docking hub or node. Here it's I should say a berthing hub. I should explain the semantic difference. I slip up myself occasionally, but berthing always implies a soft docking, something that happens very slowly and at a very controlled rate of velocity. Docking implies the possibility for absorbing some energy on impact, and in fact all the Apollo dockings were essentially hard dockings in that we were attenuating energy with absorbing springs pedal structures. And then this is another geometry here, using the hemisphere to create an airlock. We looked at mechanisms a lot. This is another variation using a pressurized power module. I looked a great deal at the whole issue of berthing mechanisms in developing the triangular tetrahedral concept. And it was really impossible to make that work without coming up with a completely new concept of berthing modules together. The current paradigm for berthing is based on the Apollo-Soyuz test project, where we had axial docking. And I'll go into that a little more later. Oh, here you see the geometry of one of those hubs. In this case, it's constructed out of hexagonal gores. And I think in this particular variation, there are 14 hexagonal gores and a few small rhombic filler panels. And this is the geometry that supports one type of tetrahedral geometry. On the right, you see, you see the Apollo docking situation, where here we see a view of the Apollo command module from the lunar orbiter, the lunar module. And on the right, you see the lunar module itself. Let me get a closer look at this. Okay, you see a cutaway view here of the Apollo command module. The docking passes into the orbit, into the lunar insertion module. This is actually a relatively early version of the lunar module. But you can see what happens is the docking is linear on axis on a single vector. They control it from 6 degrees of freedom as best they can. For space station, we want to avoid hard docking, and we want to be able to make very complex utility connections across the connections. And I make a distinction for space station between berthing modules together to each other or to docking nodes or hubs, and docking to the orbiter at a docking tunnel that will be attached to the airlock. So I began research using my fabulous budget, and I started with the assumption that if you had a docking hub, that you would have it dedicated to all docking functions on it, all active mechanisms on it. And so in this little model, you see modules berthed or not berthed, or detached from the hub. And what basically I learned from this was that you have two problems. First of all, it very quickly becomes quite crowded around that hub when you start putting these things on, if we're talking about 14 connecting ports. Also, I learned a principle, which is that the more active a mechanism is, the more unidirectional it tends to be in this case. And here we're working with kind of a lateral slip-in idea, which is really the only way to achieve the triangular geometry. I moved up the scale to cabinet hardware from Sears with rubber bands, And this is a slightly different geometry than a pure triangle, and that these are kind of embedded. But this is the first one where I put the active mechanism on the module itself, and it had the passive mechanism, or the passive side, on the hub. And this is not yet truly omnidirectional, but it's moving in that direction. So then I use some really high technology here. And whenever I go into that hardware store, they still look at me strangely. But basically, what this is a model I developed to demonstrate what I call multiple vector sequential berthing instead of single vector simultaneous alignment docking. And what you see here on the right, a diagram. I'll just take you through the steps on this cartoon and then through the sequence with the model. Basically, what happens is that the first step is that you align the modules axially and slip them into a clamp. The clamp is closed and it's latched loosely. There's the clamp. And the model, it's possible to rotate the modules relative to each other to align the internal utility connections. The clamp is then tightly secured. Pressure seal is made at the clamp, which is conventional high pressure clamping. Something I picked up in the wind tunnel world. And once that pressure seal is made, it's possible to pressurize it and join the joint and make utility connections manually. So to go through this sequence, here you see the module separate from the nodes or hubs, which are secured in space by a beautiful redwood truss. And let's see, on the right we've aligned the module axis, and with the clamps, we've closed it loosely but still allowing rotation. Clamp them to make a secure pressure seal once we have it where we want it. I mean, to make a secure structural connection once we have it where we want it. And within that joint, making a pressure seal between the flanges. So there you see it all buttoned up on the right. And this is a set of sections from the patent drawings. I'm pleased to announce that just last week we received from a patent office their response to this, and of my 25 claims, they allowed me one, which is for this utility channel. That's okay. Actually, it's the first time I've ever been allowed a claim on the first application. All my other patents have come, all two of them have been one on appeal of disallowed claims. So I guess I'm getting better. I expect to pick up a number of those other claims on appeal simply because they didn't really understand what they were looking at. But anyway, so you see here the clamp. In this case, I'm showing a tripartite clamp arrangement. Utility channel. This is a screw servo mechanism to drive down the clamp and close it. This is the only claim I won't get. The patent office unearthed a Soviet patent from 1973 with an almost identical mechanism, but you can't have everything. And anyway, cross sections showing those. So utility connections are really a key. Actually, the one claim that's been allowed is on this utility connection channel you see right here. What happens is that you see the cylindrical section of this joint. The channels are laid in around the internal perimeter. It's a pre-assembled channel that's carried internal to the module and then brought up and installed within the joint. And the length of this can really vary anywhere from a foot or so to 6 or 7 feet if you needed it. And the utilities issue is turning out to be an incredible, difficult issue, just making the connections between the modules and distributing them. We anticipate that we'll have 15 to 18 different types of utilities passing from one module to another. This includes power, data lines, both electrical and optical perhaps, various types of communication signals, water, clean water, drinking water, gray water, gases for propellants, cryogenics, and so on. A few of those will probably be external, particularly the cryogenics and the thermal cooling, the major thermal buses, but local cooling might run through run through the bulkheads and so on. It's really a difficult problem to run those through between modules. And we also studied the whole issue of remote automatically actuated connections versus manual connections, and came up with an interesting study there. I don't know if I have the chart on that in this carousel, but we'll see. This is a display of utility complexity. These are motor control conduits. This is something part of a system we put together in one of our wind tunnel projects. This is just power distribution, and I had a piece of this routing them. They come out here parallel. I picked them up right where they came out and routed them around several hundred feet of twists and turns to come up in the right place. Actually, we had to make the contractor recut his holes twice to get them in the right place. And here you see just another section, cartoon with the utility channel laid in place. A transverse section. Here you see, here's the analysis. What we found was with the remote actuated connectors being widely proposed by the contractors, that there's an incredible amount of money in automating little things like this. But things like this are the easiest things to automate, you know. But that doesn't mean that's the thing you should automate. It's very hard to get this point across to people who are infatuated with robotics. What I found is if you have a remote actuated connection here, you have 5 potential lead points. You have leaving the pressure bulkhead on one side, entering the actuator, between halves of the actuator, out the other side into the pressure bulkhead. In the manual connection channel that I've showed you, basically have 2 lead points, just where you pass through the bulkhead. One of the reasons I say only 2 is because you can test this channel on the ground with a very high degree of reliability. You can't test these channels for slop and misalignment and thermal stresses and so on. When you're in orbit, you just have to use it and hope it doesn't leak. So what this shows me is that you could spend a whole lot more money, I mean like orders of magnitude more money, to have a system that's much less reliable and requires roughly 2.5 times as much maintenance. So when anybody talks to you about how we want to have a totally robotic space station and the man-tended space station and everything is going to run by itself, you have to look at that very critically. So what are they really talking about? The way I look at this as an analogy to Earth architecture or construction is, suppose you're laying a sewer pipe in a trench. You dig a trench, you put a robot down in there to connect your sewer pipe. You connect one pipe, then you pour the concrete with the robot still in the hole. That's this type of proposal which has come time and again from the major aerospace contractors. And ultimately we got down to, I got down to this level of detail. For these are embeds in the pressure walls for electrical and gas connectors. And the only interesting feature there is that they use ring bearings. They're not that much different from conventional aircraft disconnects, except that they use some bearings to just enhance the ability to turn them. Whoops, wrong one. Okay, function. It's most common to talk about function when you start a talk. You start talking about function, what is the purpose, and so on. But I've held it to the end of this section because of the problem of really defining what is function. What is how do you clarify? What is the clarity of a function? Where does function start or stop and form begin? How do you organize your functions? Ultimately, for space station, we have 2 big questions, which are: do functions equate to modules, and can function dictate geometry? And I, basically am familiar with the concepts of functionality advanced by Louis Sullivan, who was really quoting Horatio Greenough when he said, "Form follows function." In some cases, that's true. And here, it's much more complex, and in a lot of cases, form and function are inseparable. In some cases, there's no relationship whatever between form and function. So here you see three of those geometries I showed you earlier. I can't believe there are no questions so far. I can't believe everyone is really getting all of this. But anyway, we must have picked a really good school for this grant. Anyhow, we have here a very simple idea of comparison of a tetrahedron to a cube. The tetrahedron is the smallest, is the simplest platonic or regular solid. It's self-rigidizing. You have rigid strut members with joints that do not resist any moments or torques. They're just pin joints. Here, you see a cube, and as you should know, a cube has no inherent rigidity unless you make the corners very stiff so that they translate moments, or you brace three of the sides to create rigid diaphragms. And so when we look at space station structures, we've been seeing a lot of rectangulated structures where we end up having to do a lot of bracing or stiffening or carry tremendous loads through the docking connections. The triangular configuration, we don't have to do that. Some of the other functional issues, and I'm just going to give you a range of these issues, are contamination from plume impingement from the orbiter thrusters. This is a computer graphic diagram of plume impingement from the orbiter at two different approaches to the station and different distances. And these are basically isobars of plume impingement pressure. The major issue here is not that it might push the space station away from the orbiter when docking, but that these plumes will condense at varying densities on the surfaces of the space station and create serious problems for solar array surfaces, windows, and any sensitive instruments that might be there. And here you see just certain aspects of the configurations. Here you see the triangle with radiators on them, external radiators represented, and a raft configuration. Just looking at different approaches to the relation of form and function. This slide shows the tetrahedral configuration with three tetrahedra joined together. I believe it's 6 hubs and 12 modules. One of the things you'll note with this system is that as you add modules and nodes, you get an improving efficiency. You get an economy of agglomeration where as you go along, you need fewer hubs per module. And that's a model I made in the shop. And actually, I should explain how serendipitous this model was. I made this model before I really had figured out the berthing connection. I knew we had to have something to do that, but I really didn't have a solution. And the way I did this was, we didn't have the funding to make a precision jig fixture to do this on a wing properly. So what I did was I made a paper template, and I drew the locations to drill holes on here, and it was given to an apprentice in our machine shop. They wouldn't let me do it because of insurance limitations and so on. But anyway, the hubs were not precision drilled. All of these things are off by a degree or 2 degrees or 3 degrees. And what it meant was that when you line these things up with I used the plexiglass dowels and put aluminum ring separators just to spread them apart. It just didn't join together properly at first. So what I did was I found myself rotating each of the modules until I could get one triangle line and then try the other. And eventually, through trial and error, I managed to rotate all the modules to get those alignments. And I thought, well, this is really a drag. I mean, what happens if we have this problem on the space station where the thing doesn't line up, if something's out of right angle or out of true? How are you going to handle that? And it was from there that I got the eureka moment to go to the toilet bowl model you saw with that rotation. Instead of worrying about it, plan for it. Plan for rotation around those axes and separate all the functions by vector, separate them all sequentially in time so that no one function is dependent on something else happening simultaneously. And this puts a whole other type of safety buffer within the whole system. And here's another view of the orbiter. This is a cheap orbiter. I should say it's cheap because it doesn't have the overhead flight deck windows. This is available in the Ames cafeteria for $6 a copy, made in Singapore. And anyway, here you see the aft flight deck windows, which are really quite significant. Viewing angle is very significant here, as is the cone of approach, the docking cone of approach to the orbiter. One of the advantages of a reverse cone of approach, such as you see here, is that rather than docking up against a flat surface, what you can actually do is you're docking against an object that recedes away from the orbiter. Let me just go back one. Yeah, there you can see it a little better. You can dock up against a point rather than on some of the other configurations. You're docking against a planar surface. So there's a lot greater latitude for error in terms of the orbiter swinging around. And got into a lot of detailed studies of what really goes on with minor variations in the hub geometry. One of the limiting factors I ran into with this for the present program is that there's a conflict, just a pure dimensional conflict between the hatch diameter and the amount of surface that we have to put it in. I forget what size. I think these are about 3 foot or less diameter hatches. And in the space station program, we kind of shot ourselves in the foot because I personally was arguing for larger and larger hatches, never realizing at the time that it was going to make this hub impossible, at least with the shell that would fit in the orbiter cargo bay with the external docking mechanisms attached. And right now, the reference configuration is carrying a 50-inch diameter hatch. The shuttle has a 40-inch diameter hatch. And there are memoranda floating around in Johnson Space Center for a 60-inch diameter hatch, and I just heard that there's at least one trade study at Marshall Space Flight Center for an 80-inch hatch, and I don't know how we'll accommodate that at all. But this is this kind of thing that ends up squeezing out decisions when you run into these dimensional limits. The cargo bay is really an incredibly constraining delivery truck, and this is one of the most curious things about designing for this program, which is that we are really limited in a very profound way by the delivery truck. We had much larger habitable modules potential with the Saturn V class of rocket. We could go up to a 21-foot diameter, even a 25-foot diameter would have been no real significant problem. But here we're living and working with these very tight modules. Yes.
Airlocks, all the airlocks for EVAs are going to be within the habitability modules, not within these connecting nodes, right?
Well, that's an interesting question, which I will deal with in painful detail tomorrow. But right now, we are engaged in a trade study of whether we should have an internal airlock or an external airlock. And there's a very bizarre political loading on that, which is that at present, everything that's internal to a common module outfitting as part of the Marshall Space Flight Center package, but only if it's internal. And right now they have an internal airlock in Work Package 2. The contractors for that are Boeing and Martin Marietta. However, it's incredibly impractical because the airlock is really quite large, consumes an enormous amount of volume, creates a lot of problems. But if we decide to go to an external airlock, which is one of the things that's shown in the reference configuration, it's not the only way to go within the reference configuration, but it's one of the options. If we were to have a decision to go with an external airlock, it would mean that the airlock work would move to Johnson Space Center. So Marshall is fighting tooth and nail to keep an internal airlock, so they keep that piece of the project. If, however, as I see it, the airlock were to be Marshall Space Flight Center's, regardless of whether it was internal or external, they would decide in less than 1 minute to make it external. because it's creating so many problems for them, but they're not prepared to give it up voluntarily. Anyway, this is a computer movie from Johnson Space Center which shows assembly and construction of the space station. The remote manipulator arm picking, in this case, a cubical docking hub. This is a hub developed by Maynard Dalton. Picking it up, moving it into position, and attaching it. And what is disappearing behind here is a radiator structure. I think this is the big T configuration. And here you see from the patent drawing the workshop module with a remote manipulator workstation to do that from the station rather than from the orbiter. It's really rather unlikely that we'll use the orbiter remote manipulator very much to do station construction. A lot of problems associated with that. Here you see a side view of that sort of computer movie. On the right you see the assembly sequence that I proposed for the triangular tetrahedral one. And this is really kind of a rhetorical diagram. But what basically I was trying to get at was the idea that the center of gravity of this and how you develop your symmetry relative to that center of gravity is quite critical. The general assumption that we have had in the program is that you start with something that's small and relatively compact and manageable, and as it gets larger, it just grows and grows and becomes huge and immense, and you start having all these very complex programs of attitude control, stability, and dynamics, and you do this very sophisticated programming for your reaction control system, and it just becomes this monstrosity, but it's a control stability versus dream or weather or whatever. I took the approach that at the smaller amount of mass early on, we can tolerate the greatest amount of eccentricity, the departure or divergence of the center of gravity from the center of symmetry. And as the station grows to some resolution or completion, we would aim toward the symmetry. And so what happens is as you follow number 200, which is the center of gravity, through this build-up sequence, you see that it moves closer and closer to some sort of center. So finally, it's right dead center of this planar triangular configuration. And I even go so far as to take a solar array from its original position and relocate it, which is an absolutely horrible thing to do in terms of structural dynamics and attitude stability. However, I wish to make a point about the ability to relocate to create that symmetry. And I forget who it was, but somebody asked me this at one time, was this because of a classical training in architecture? And I really don't know whether it came from that or just from common sense. But that, I guess you could read Vola v. Compton to that or something. I don't know. So, as we approached the development of the reference configuration, there were a number of concepts that were presented at Johnson Space Center and elsewhere. And these are just a few of them that I'll show you. This is the big T in its initial configuration and growth configuration. The modules are down here at the bottom somewhere. Right there. And you see it builds up to including more modules. And after I made the first presentation of the triangular tetrahedral thing at Williamsburg, a few months later, a lot of people were using working nodes, although they were still locked into a cubical idea. They're still doing with right angle geometry with cubical hubs. And the cubical hubs would have to transfer moments to make this thing rigid. So then what we get is the big space truss, the big space structures, people coming in and saying, well, obviously you need a truss to take out all those structural loads. And that's what you get with these big trusses. In this case, the solar array is on top. These are radiators underneath, and more radiator surfaces orthogonal to that. And we also have orbital transfer vehicle hangars there in the growth version of that. And we see similar build-ups for the so-called building block configuration, which is another rectangulated thing, this time without the truss. This is the most common sort of thing we saw for a long time. Really has a lot of weaknesses. Here they're using hubs also, somewhat cubical, at least they're 90-degree right angle hubs. And basically the same sort of attachments as on the previous one. And finally, we have the delta configuration, which is a phenomenally huge truss structure. The people who designed this in Houston assure me that they have figured out how to package this whole thing to fit into one payload or less on the shuttle orbiter cargo bay. And I'm waiting eagerly to see them do that, if only for the learning experience. And I'm a great fan of space race and things like that, but this is going to be totally deployed out of one folded up package. It's really going to be amazing. But anyway, they have consolidated all their modules down to one central location on the lower apex of this. You may remember in the earlier versions of this, we had one module or chain of modules at each of the corners with very long connecting tunnels. So they decided to adopt a little bit of human factors input and reduce their circulation paths. And if you look closely at these modules, at these hubs, you will see that we have 5 ports. 3 of them are radial at 120 degrees from each other to accommodate the 60-degree geometry. And where did you see those hubs before? As it turns out, I had lunch with these guys about 2.5 months before they published this. But you don't get no credit. Anyway, this is their sort of working drawing on that, and this is one of my sketches for 120-degree ports. All right, let me talk a little bit about habitable interiors. Oddly enough, I haven't really done a lot of work so far in the habitability areas. We have some other people doing that. I've been really working a lot of the functional issues instead, which I feel equally comfortable with. But curiously, they're functional issues that nobody else was devoting any attention to, the ones that I've selected. So at least I'm not fighting from the outset for the turf, but it's still a tremendous battle to persuade people once you've done the work that it should be included. So this is a mock-up at Marshall that was done in the early 70s of Skylab, the crew deck, and the wardroom and its dining table. This was the area in which Raymond Loewy and Loewy Snaith had the greatest amount of input. And some of the people who worked in their firm are continuing to be involved. Fred Torg was the lead job captain for them, and he is continuing to have input. He works for the firm of Sundberg Farrar Industrial Design. And then there's another fellow, John Franzanito, who works out of Austin, who was involved at the time. And they have just unveiled in Manned Systems Division a central beam mock-up, which is well worth seeing if you are going to take a trip to Houston. Some of the influence of Loewy Snaith were these hexagonal sort of tables, and the wardroom table, some of the locker configurations. Most interesting thing in this really are the sleeping compartments, which are here. Fortunately, the slide got cut off on reproduction, but curious design decision that they made, which is that you have 3 crew members up there, and you would just assume that if you have 3 people and they're approximately their peers, their equals, you would give them essentially equal or identical sleeping quarters. Well, that's not what they did. They individualized them. They're all different, slightly different shapes, or even slightly different floor areas, as a way of making some type of statement that there's something special about the private space. However small that private space is, there's something inherently special about it. It's not like, cutting off slices of bread or something. Very interesting decision. And right now what we're seeing in the current space station program is a repetition of the whole business of having identical crew quarters modules, and maybe we will, or crew quarters compartments. Maybe that's the way we'll end up going. But one of the most enlightening things that came out of the Skylab design was that One of the other interesting things is this ISO grid, the 60-degree equilateral ISO grid that was used for the floor and ceiling. This was a restraint grid. They had they had triangular shoes with metal triangles on the bottoms that they could slip into the grid, lock themselves, and turn them and lock into position and then release. This was actually developed by a fellow named Oliver Harwood, who is now working at Rockwell. I think at the time he worked for McDonnell Douglas, but I'm not sure. Anyway, that's often attributed to Loie Snaith, but in fact it's Ollie Harwood's. Now this is a mock-up that was built at Boeing in 1982. I'm not going to dwell real heavily on mock-ups in either of these lectures. I've taken a lot of slides of mock-ups. I think they're worth doing. They're a lot of fun, but oftentimes what they're used for is to institutionalize prejudices. None of the corporate mock-ups that you can see at any of the major aerospace contractors are really research mock-ups by and large. What they are is they're demonstrations of preconceived ideas. This is a case in point at Boeing, although as far as mock-ups go, they've done some very interesting things here. This was done for the Space Operations Center study in 1982. One of the most interesting features that came out of this, and the architect for this was Brand Griffin, who has just made the big move to Huntsville, Alabama, is that he put the docking port off-center. He was the first person ever to do this, as far as I know. And it has a very interesting effect of allowing you a larger and usable volume for a workstation or observation station. Now, in this case, we have a rectangulated cab, and I'll have a lot more to say about end cap geometry tomorrow night. But this is an interesting plywood mock-up. I should say the other one, whoops, wrong way. The other one, whoops, there it is. The other one represents a so-called revolver type of thing where you have crew quarters that are like pie slices. That's a very crude version of it. Every single contractor has that thing, and they're all sort of equally deficient. On the left, you see B.J. Bluth, who's kind of the lead space sociologist in the world. Inside one of the crew quarters, Brand put together in conjunction with Dick Olson. Dick Olson's an industrial designer in-house at Boeing who's probably the single most influential aircraft designer in the world in terms of aircraft interiors. He's worked on every Boeing plane since the 707 in a position of responsibility. And anyway, this is a private crew quarter. The sleep restraint would be on the left here. There's a little private desk and video screen and a private porthole to look out your own little window. This is a so-called personal hygiene facility with some type of hand washing facility represented by this dome and a zero-gravity toilet idea with hip restraints that hook in to hold your hips passively. And we've had a very interesting cycle in terms of the human factors design on these toilets. And sometimes it's really amazing that lessons that are learned one time are totally lost the next time we go around. What happened on, what we had on Skylab was that the toilet was actually placed on the wall horizontally, I mean, in the side of the wall, vertically in the side of the wall, but it had two hand restraints. It doesn't matter in zero-G which surface it's on, but there were two handholds so the astronaut could hold himself down in position. The original shuttle toilet was designed without any restraints at all, and when the first crews flew on the Columbia, they found they had to press their arms against the sides of the compartment to hold themselves in position, and it was a remarkably unsatisfactory arrangement combined with the inadequate vacuum suction in the unit. It was really a mess, and General Electric is still trying to make the thing work properly, although on the last two flights I have heard there were no serious anomalies. We made up for it with the monkey food and rat turds. Anyway, so no, there won't be that many of them. There might be two total on the entire station, although the issue of whether it should be centrally located is a very major issue. In the concept development group baseline, what was proposed, the idea was actually originally Al Chambers' who was my division chief at the time at Ames. I believe he was the person who thought it up first in one of the brainstorming sessions. The idea was to put that in the logistics module. You'd put the toilet in this logistics module so that you didn't have to pump the sewage around. You'd have it right there. You could control contamination, control odors, clean it once every 90 days whenever you brought that logistics module down and replace it with another one. You know, if we're going to have this thing on orbit for 10, 15, 20 years, and we need to clean it regularly, we're going to be very limited. We're going to have a serious set of concerns because we are quite limited in the number of cleaning agents we can use. Your ordinary household cleaners will knock out the activated carbon filters that are used currently for filtering air on the shuttle, and we don't really have any better technology for that yet. So your ability to use any sort of solvent is very, very constrained. You've got to worry about toxicity built up because everything that's dumped into the atmosphere essentially stays there. It's very difficult to remove a lot of these types of solvents and their fumes. Anyway, this is another view of that crew quarters module with a sleep restraint drawn by Brand. And this is a view of the interior of the module. And you know, this is an interesting thing. This is a tour group. This slide got out of whack somehow. But what you see here is the clearance between these compartments and how tight the interior is. On the right there, you see a straight-on view of that personal hygiene unit. Now, over here on the, well, let's see, on the right, I guess that's somebody opening the window. Yeah, it's Roy Courtney, who was the leader of the Common Module Study Group, opening that hatch and looking out at the Earth, which of course is right there. And this is the interior of the workstation cab on the Boeing mock-up. And what it really is it's a replication of the shuttle aft flight deck with the overhead windows and forward windows, so 3 of them instead of 2 in this case, and a couple of side windows. And we've researched the whole issue of windows for proximity operations very thoroughly. We hope it's thorough, and have a lot to say about that. That's somebody else's slide. Anyway, goodness, I must have put the wrong slide in. That's one of your slides. Anyway, on the right there, you see a study of these NCAPs, various NCAP concepts of Boeing from the left, Boeing, Lockheed, and JSC concept, and then two concepts that derive from the triangular tetrahedral, which using these hexagonal boards allows us to get larger window surfaces. This is really bizarre. That's upside down. Okay, here's the reference configuration. I'll talk tomorrow more about some of the mock-up activities we have at Ames. This is what we call the space station reference configuration, and it's the baseline around which we're working. We are asking the contractors to offer us alternatives to this configuration or improvements, and it kind of represents a standard to which we've all agreed, at least for the next 2 years, to play by the rules of the game, which is what we as a research center are doing. Traditionally, a research center is chartered to look 10 to 15 years ahead into the future requirements of the agency, so that a lot of the stuff we do is not easy to tie in directly to a current program, even at the beginning of that program. But a lot of the research we're doing now are trying to make as timely and relevant as possible, except that it must also, for the purposes of our management, clearly demonstrate that it looks far into the future as well. But anyway, the characteristics of this reference configuration, which you'll learn more about tomorrow, are the 4 modules here grouped together in a kind of a basket weave pattern with 1 radial port segment on each and dock an end port into that logistics module, showing 2 external airlocks here. This antenna structure represents the large deployable reflecting telescope, which is an Ames project to build a 20 to 30 meter radio telescope or actually it's an infrared astronomy telescope. Yeah, there's a proposal for something like 100-meter diameter radio telescope to be built on the station, but I think we're really a long way off of pulling that off seriously. This is the truss structure, the large box truss. In this version, we're looking at about a 9-foot cross section, orbital transfer vehicle hangar, various types of restraining points for satellites or vehicles, co-orbiting platform up there, and upward-looking payloads. One of the major issues that we're thrashing out is whether we can really have any astronomical payloads on the station. The station itself will fly in gravity-graded Earth inertial mode. That means it flies the heavy part pointing down towards the center of the Earth, and the line running up through the center of gravity of the station. The shuttle itself is most stable, flying in gravity gradient mode. The center of gravity of the shuttle is down here near the tail where the engines are. And although we are not strictly speaking weight limited in the shuttle, I mean, the volume limitation is much more critical. When we start putting large homogeneous loads into the cargo bay, we start developing some problems with displacing that center of gravity outside the allowable envelope. We're raising some suggestions that you pack all the equipment in a module at one end, almost as ballast, put that in down towards the bottom, and then once you got up on orbit, you would relocate it. These are the solar arrays. They're fairly straightforward. They're gimbaled in two axes or 2 degrees of freedom. And the remote manipulator arm that can travel around the station, so-called mobile remote manipulator arm that presumably will be built by the Canadians. Anyway, that's where we are right now, and we're working around this reference configuration. And tomorrow night I will be showing you some specific studies we're doing on airlocks, windows, and spatial orientation around this configuration. So that basically concludes the slideshow, and I'll take any questions you have.
What type of orientation are they looking at in this configuration?
What do you mean orientation?
Up and down references within the module that you're talking about?
Come back tomorrow night. It's right now we're trying to solve that problem. I don't mean to be snide. Basically, it hasn't really been thought out. The most common assumption you have is that down is is down towards the Earth and up is away from it. However, I can demonstrate quite readily that for certain operations, you have to break out of that reference coordinate, or you create too much conflict. Yeah, Steve?
Marc, what are you doing about contamination of the solar arrays if you do large amounts of material processing contaminants?
Well, hopefully the materials processing contaminants are all contained within whatever equipment we fly. And what the current flight protocol is, if there's any detection of any leakage from anything, even if it's just a shorting wire, they just turn the thing off for the duration of the flight. However, there's very serious problems with contamination from propellants, from both the oxygen and hydrogen, and also from hydrazine that will be used in the orbital transfer vehicles. One of the things that happens with hydrazine if it leaks in hard vacuum is that it turns into a sort of a white snow which settles or sticks to cold surfaces, and that's a very serious problem for the solar arrays. And right now, as far as I know, there are no good solutions to that.
Is there any preference as far as structures, as far as your moments of inertia, large moments of inertia, using up your attitude control?
There are a lot of issues around that. There was a very extensive discussion in Houston 2 weeks ago in the advanced development about attitude control and stabilization. We're going to be flying with a mixture of control moment gyros and gravity gradient, trying to balance with aero counter torques. That means that as the station flies, there's a certain amount of drag on the station from free molecular oxygen. Even up at that height, there's a thin atmosphere that has a measurable drag, and the idea is to try to use that to help stabilize the station in the gravity gradient mode. But The truth is that you know, if you let the controls engineers design it, you would use enormous amounts of propellant all the time and constantly adjust every second or so. So we've got to have a happy medium.
I've got a question about the big T mark. One of the things that's been intriguing me about them is when you talk about the issue of fail-safe design, you've got one group of sort of heavily high-mass things at one end and one group at the other, and connecting the two, you've got essentially a rectilinear tower with what is the equivalent of 4 beams. Now, if you lose any 2 of those beams through any kind of accident, you're going to get some kind of injury. Is that hardly a? I mean, that.
Well, actually, right now, the truth is that the single most blatant single-point failure mode we have is if an orbital transfer vehicle or the shuttle should fly through that truss and cut it in half. And right now we have that. Just in the reference configuration, we have the single truss. It's 9-foot cross section, whether it's a box truss or a tetrahedral truss or whatever. And we discussed that. I discussed that in Houston, and we just discussed it today at Rockwell. And right now, we're kind of at the position where none of the contractors yet have gotten up quite gotten the guts to stand up and say, you have a serious problem here with this reference configuration, and we recommend that you solve it by putting in 2 more trusses offset from each other as strong backs or something like that. You know, I think if we continue with the power tower, we've obviously got to have more redundancy there. Yes?
Did your tetrahedral arrangement actually eliminate the need for trusses? I think I saw one.
Yeah, well...
And wouldn't that be a big advantage?
It did not eliminate the need for trusses. What it did was eliminated the need to have a truss to take structural moments and torques out of the docking joints. You would need a truss to attach external payloads, to run certain types of utilities, to run your power lines from a solar array. One of the good decisions that we've seen associated with the power tower is the idea of taking the moments from the solar array, not running those through your docking connections, but running those through a large truss which can handle them without imposing a lot of structural penalty there. But for module to module connection, there's absolutely no reason why we should have to put in a big fat truss to connect module to module, as I see it. Was there a question back there before?
This might be a very naive question. I don't have much space background, but has there been any work done in inflatables in terms of things coming out of the cargo bay? I mean, it seems like you could increase the size of easily.
There's been a lot of proposals for using inflatables. The first proposal I've been able to find was made by the Austrian group that Haus Rucker spun off of. I forget their name, but they just recently published a book on inflatables. God, I lost their name, but anyway, there have been proposals after proposals to use inflatables, and the problem you have with inflatables is that you're worried about meteoroid puncture, debris puncture, erosion by molecular oxygen, thermal stresses, all these hazards that are what drive the reliability, maintainability, quality assurance, and all that stuff. However, I think we will see some use of inflatables. Certainly we right now have a rubber tunnel in the space shuttle made by Goodyear or Goodrich or somebody like that, which connects the airlock to the space lab. It's pneumatic. I should say that all architecture in space is pneumatic. You always have a pressure vessel that's holding pressure against the vacuum. So in a sense, everything is inflatable, except you sort of inflated it on the ground. And it's really a matter of how much stress that can hold. Yes?
What does a meteor do when it hits something like a regular space station?
All right. Well, actually, we're much more concerned with space debris impact than we are with meteoroids. We have had meteoroid hits on spacecraft. We've never had any serious damage. The orbiter has been hit twice on the windows by some very small particles that have required replacement of the windows. And the Soviets reported a measurable hit on one of their windows on Salyut 7.
What are these hits like? Are they like
Well, we're talking sub-millimeter particles here in terms of what we've had, but what the environment is, we anticipate a hit by a 1 millimeter particle once a year on the reference configuration. That's the baseline estimate. The space debris particle population has been studied in quite a lot of detail by a fellow named Don Kessler at Johnson Space Center. And the breakdown is that there are particles that range in size from sub-millimeter up to quite large pieces of like delta upper stage boosters. The problem we have is that there's a middle range we have trouble figuring out how to deal with. The lower end of the spectrum, which is, say, sub-millimeter, maybe up to 1 centimeter, but that's really going some. It may be possible to apply bumpers to the exterior of the spacecraft to break those up or absorb their energy sufficiently. We're talking about particles that are moving at like 15 kilometers a second. The spacecraft, of course, is moving at a similar velocity. So if there's a convergence, your net vector is not 15 kilometers per second. But even if you're dealing at 1 kilometer per second, you've got quite an impact. You've got a tremendous momentum of impact there. Theoretically, NORAD is tracking everything that is 10 centimeters or larger. That's 4 inches or larger is theoretically right now being tracked, and NORAD knows where everything is. Interestingly enough, the majority of those particles are from American upper stage boosters, and the rest are from Soviet spacecraft. Very small amount from anti-satellite testing so far. Theoretically, there's a measure of what the population is from force between 4 centimeters and 10. We don't know where every particle is, but we have an idea of where they are and how many there are and where they're moving. And theoretically, I preface all these statements with theoretically, you'll notice. Theoretically, we can detect those and navigate around those. In the range between 1 centimeter and 4 centimeters, we can't detect them, we can't track them, we can't defend against them with any sort of bumper. And it may be really more like between 1 millimeter and 4 centimeters, realistically, maybe half a centimeter and 4 centimeters. And it's a big question, we don't know. At what point do you say that you accept the loss if you get a hit? Those particles are relatively rare. The great majority of particles are in the sub-millimeter range. But it's a very complex phenomenon, and Don Kessler's developing what he calls hypervelocity impact equations to predict what happens. But basically what happens when you get an impact on a metal structure is that if you get a penetration, you get a spalling off the backside of about 100 times the mass of the particle that hits. So you essentially have an effect like a grenade exploding on the wall of the structure. If you have a plastic composite structure, that will tend to absorb a lot of the energy. However, it absorbs the energy by delaminating, and as such isn't particularly good for a pressure vessel, because then you can't really inspect it afterwards or repair it. So you have no way of telling with any high degree of precision how far the delamination has spread through the structure. In any case, you've got to cut out a huge piece and replace it, which is obviously not practical.